Welcome to another lecture in the course on 3G, 4G wireless communication systems. In the last lecture, we had looked at the beginnings or an introduction to orthogonal frequency division multiplexing. We said multi-carrier modulation employs a bank of modulators which is very complex. Hence, to reduce the complexity, what we had done is we had used an idea proposed by Weinstein and Ebert and successfully replaced that bank of modulators by a sampling operation which is nothing but an IFFT. Hence, we said that the bank of modulators can be replaced by an IFFT operation. Following that, we said that this idea was originally proposed by Weinstein and Ebert in their 1971 paper. Following that, we said the schematic of an OFDM system is now simple. I do not have a bank of modulators anymore. I have a simple serial to parallel demultiplexing followed by an n-point IFFT followed by a parallel to serial conversion. Following that, we said that the first symbol corresponding to the current OFDM symbol block, let us say we consider transmission of an OFDM symbol. Hence, there is inter-symbol interference from the previous transmitted OFDM samples, right. So, to avoid this problem, what we said was that we are going to use what is known as a cyclic prefix. What we are going to do is we are going to take a set of symbols or set of samples, that is the trailing set of samples from the OFDM symbol. Now, the OFDM symbol consists, remember, of n samples 0 to n minus 1. We are going to take the trailing set of samples and prefix them in front of the OFDM symbol. This is known as the addition of a cyclic prefix. What that happens is, as you can see, as soon as I add that cyclic prefix, now the inter-symbol interference, inter-OFDM symbol interference is not from the previous OFDM symbol anymore, but it is from the current OFDM symbol itself. Hence, what we have is that we showed last time that the convolution across the channel is actually converted to a circular convolution, and these are the n samples of the current OFDM symbol. Okay. And as a result of the circular convolution, I have y, which is channel H, circularly convolved with x. What can be done, what can be said now is that if I take the n-point DFT or FFT at the receiver, what I have now is that yk, which is the received symbol across the kth subcarrier, which corresponds to the kth DFT point, is now hk, that is the DFT of the channel, times xk, which is the nothing but the transmitted information symbols. These are known as the information symbols loaded onto the subcarriers. All right. Hence, we have an elegant system in which yk, that is the received symbol across the kth subcarrier, depends on hk times xk, where hk is the channel coefficient, xk is the transmitted symbol on the kth subcarrier. Hence, what we have done is we have converted a frequency selective fading channel into a flat fading channel across the kth subcarrier, and this is very advantageous, since in the absence of OFDM, what we have is we have inter-symbol interference, where each symbol in the time domain xn is interfered by symbols in the previous. So, what OFDM does is intelligently, by adding this cyclic prefix, we have converted cyclic prefix and combining it with the multi-carrier operation, that is combining with an IFFT FFT operation. What we have converted this is we have converted this successfully, that is we have removed the inter-symbol interference and we have converted this into a flat fading channel at the receiver across each subcarrier. Okay. So, let us proceed with today's lecture. So, what we have is that we have yk equals hk times xk, that is received symbol across kth subcarrier. This is, let me emphasize again, received symbol across kth subcarrier this is the channel coefficient correspond to the kth subcarrier, this is the and this is the transmitted symbol across the kth, or the symbol that is loaded onto the kth subcarrier. This is the symbol loaded onto kth subcarrier. Remember, before transmitting the symbols, we are taking an IFFT of this transmit symbol. So each symbol can be thought of as existing in the frequency domain and as being loaded onto the kth subcarrier. We are taking the IFFT and converting these symbols from the frequency domain into the time domain. That's a simplistic way to look at it. So xk is nothing but the symbol that is loaded onto the kth subcarrier. These are the digital modulated symbols. These are BPSK, QPSK modulated symbols. All right. And as I said, as I already pointed out, that hk is nothing but the channel coefficient across the kth subcarrier, and h0, and these coefficients h0, h1, hn minus 1, these are nothing but the endpoint DFT of H0, the channel FIR filter, that is H0 up to HL minus 1, where the FFT is done after 0 padding, that is after 0 padding, since L is less than N after. So the capital H's, which are the channel coefficients across each subcarrier, are nothing but the endpoint DFT of H0, H1 up to HL minus 1, that is the channel FIR filter after 0 padding. Okay. So what we have now is that we have yk equals hk times xk. So across each subcarrier, essentially we have, across the 0th subcarrier, I can write this as y0 equals h0 times h0. I can write y1 equals h1 times x1, so on and so forth. I can write yn minus 1 equals hn minus 1 times xn minus 1. So I have converted my frequency selective channel into a set of n parallel flat fading channels. So these are my set of n So OFDM essentially helps me convert a frequency selective channel with intersymbol interference in set of parallel flat fading channels without any intersymbol interference. Hence, this also removes intersymbol interference. Hence, OFDM essentially removes the intersymbol interference. Hence, OFDM essentially removes the effect of intersymbol interference. Schematically, I can express the effect of OFDM as follows. I have a wide band channel, that is, let us say this is my wide band channel. I have one wide band channel for the transmission of information. This is nothing but also my broadband channel. This is also essentially basically the broadband channel. What I am converting this into is I am converting this into multiple parallel flat fading channels, and each is a narrow band channel. So I have a wide band channel of bandwidth B. What I am doing is I have used OFDM to convert this into a set of n parallel narrowband channels, n parallel narrowband channels. Each channel has a bandwidth b by n. So, let me write that each channel has bandwidth b by n, and each is essentially a narrowband channel, and each experiences flat fading. Each narrowband channel experiences flat fading. So, what I have done is I have taken this wide band broadband channel, and we said it is frequency selective because it is greater than the coherence bandwidth. Using OFDM, I have intelligently converted it to a set of parallel narrowband channels. Each is a narrowband channel, hence experiences flat fading, and I am transmitting information streams in parallel across this narrowband channel. That is what I have done. And let me now draw a schematic for this OFDM system with the cyclic prefix, schematic. And now this is the schematic of the OFDM system with the cyclic prefix. So, I have something extremely similar, except now I am adding the cyclic prefix. So, what I do now is I have a block for serial to parallel conversion. There is an input of a serial data stream which I am converting into a parallel data stream. Subsequent to the conversion, what I am going to do is I am going to load them onto the subcarriers, and similar to earlier I am going to take the IFFT. This is IFFT of data, and in fact this is n point IFFT corresponding to the n subcarriers. Subsequently, I am going to convert this into a serial stream of data. So, this is the parallel to serial or multiplexing operation. Following this is the key operation, which is the new aspect, which is essentially I am going to add the cyclic prefix. So, following this I am going to add the cyclic prefix. This is previous to transmission on the channel. So, this is addition of CP, and then I am going to transmit over channel. So, this I am going to transmit over channel. So, the new block essentially is this block over here, which corresponds to addition of the cyclic prefix. This new block corresponds to addition of the and we said this block is the key block to limit the intersymbol interference to symbols of the same OFDM symbol, which essentially results in the performance gains at the receiver. All right. So, this is the transmission schematic with the addition of the cyclic prefix. All right. So, how does the receiver schematic corresponding to this thing look like? So, what is the receiver schematic? So, how does, so this I will also write, this is the transmitter schematic. So, this is the transmitter This is the transmitter schematic. And how does the corresponding receiver schematic look with the addition of the cyclic prefix? And that looks as follows. So, at the serial data stream that I am receiving, since I have added the cyclic prefix, correspondingly I will remove the this is the cyclic prefix removal, which experiences the intersymbol interference. Remember, the early part of the symbol experiences intersymbol interference. So, corresponding to that part, I will remove the cyclic prefix. So, this is the cyclic prefix removal block. Following this, I will convert it into a parallel stream. So, following this, I will employ serial to parallel conversion, which is also a demultiplexing block. I will convert from serial to parallel. Following this, what I am going to do is, as you are familiar, I am going to do the FFT, and in fact this is the endpoint FFT. This is the FFT block. Following this, I am going to do something slightly different, which is I am going to essentially, before multiplexing, I am going to employ a detection scheme to detect these symbols. What this detection scheme is, I am going to come to shortly. So, employ detection scheme. So, I am going to employ a detection scheme to detect these symbols. Following this, I am going to convert from parallel to serial, that is I am going to multiplex and give out the serial data stream. So, parallel to serial, or this is multiplexing operation, and I am going to serial, this is converting to serial data, this converts into a serial data stream. Okay. So, I have detection scheme, I have parallel to serial conversion, which is a multiplexing scheme that converts into a serial data stream, and the new block is essentially, there are two, I think, new blocks which we haven't seen before. One is this cyclic prefix removal. This block is removal of cyclic prefix as it is subjected to ISI. Remember, cyclic prefix is the initial part of the symbol. This is subjected to intersymbol interference, hence we remove the cyclic prefix. Since, so removal cyclic prefix, since it is subjected to ISI. And then this other new block is the detection scheme. I haven't said much about it, but I am going to say something shortly, and it is very simple. This is detection of transmitted this is detection of the transmitted symbols, and this is the, now this is the receiver schematic, this is the complete receiver schematic, this is the receiver schematic of OFDM with CP. That is the most important part. Remember, this is with the addition of the cyclic prefix. Hence, this is the receiver schematic of the OFDM system with the cyclic prefix. Now, I just need to mention a little bit about this detection block. What is this detection block? Remember, across each subcarrier we have the following relation. This is the received symbol, yk is the received symbol, hk is the channel coefficient across the kth subcarrier, xk is the transmitted symbol, nk is nothing but the noise across the kth subcarrier. We haven't talked too much about this, but it is the noise across the kth subcarrier. Now remember, xk has the effect of hk, similar to a flat fading channel. Remember, we have to employ some detection scheme because this hk distorts the phase of hk. So what we can do is, one simple scheme is to simply divide yk by hk, that is simple, similar to the zero forcing receiver that we have already seen. So the one simple detection scheme. So a simple detection scheme for xk xk is to employ a simple detection scheme for xk is to employ zero forcing, in which I will do 1 over hk times, which means xk hat equals 1 over hk times yk, which is nothing but gives me xk plus nk divided by hk. This is nothing but some new noise n tilde k and so on. So this is nothing but, this is the zero forcing receiver used for detection at the OFDM receiver. This has to be done for each subcarrier. Right? What has to be done is that this process has to be done for each subcarrier. So this is the zero forcing. So let me mention that this is the zero forcing across each. So this has to be done across each subcarrier. So this is the zero forcing detection. Remember, because to remove the effect of the channel, there is a fading channel across each subcarrier, we have to employ some detection scheme at the receiver. One can employ zero forcing, which is simple. To put it simply, it is simply dividing the received symbol by the channel coefficient. That is what we are saying. Of course, if you are more little bit, one can also directly see that you need not employ dividing. You can in fact multiply by hk conjugate. So if you multiply by hk conjugate, what you have is hk conjugate yk equals mod hk square xk plus some noise n prime k, and you can clearly see in this case this is always, this is mod hk square or magnitude hk square is real number, hence this has no phase, hence it does not distort xk. However, it distorts the amplitude because it has some power, it distorts the amplitude, but it does not distort the phase. Hence, if you have a BPSK constellation, I can employ this also. This is nothing but essentially a matched filter detection. This is nothing but a matched filter detection, and remember, you cannot employ this for amplitude constellations like PAM because hk square distorts the amplitude of xk. However, it does not distort the phase. So if I have a constellation such as BPSK, QPSK, so on, I can employ it to detect phase constellation. So this can be employed for BPSK detection. So this can be employed for BPSK detection, and of course one can also be slightly more fancy and one can be slightly more involved technical, and as we said, zero forcing results in noise enhancement. Match filtering is not optimal in the case of high SNR scenarios. So what is the optimal thing? The optimal thing we already saw in the case of MIMO communication systems is the MMSE receiver, and one can naturally employ also the MMSE receiver. So let me just write that equation also. One can employ MMSE detector, and MMSE gives you better results, and the optimal detector and MMSE detector, we already know x hat k, the MMSE or x hat k MMSE is nothing but multiply h conjugate k divided by magnitude hk square plus sigma n square into yk. This we have already seen, is the MMSE receiver and it's optimal. Now you can see at high SNR it reduces to the matched filter, which is h conjugate k divided by mod hk square, which is nothing but 1 over hk. At low SNR this is simply h conjugate k divided by sigma n square, which is nothing but the matched filter. Hence this is again the same thing which is related to as we have seen in the case of MIMO. So this is the optimal at both high SNR and low SNR and doesn't result in noise enhancement. This we have already said is the MMSE receiver. This is the MMSE receiver across the kth subcarrier for OFDM. Across the kth subcarrier in this. This is now the MMSE receiver across the kth subcarrier in this OFDM system. Right. So that is what we are saying. So one can employ several detection schemes. After the detection, what you can do is essentially now convert it back into a serial stream. That is, now you can multiplex and give that serial stream back to the higher layers or whatever application is using this data. All right. So what you do is you essentially use from serial to parallel, IFFT back to serial, add the cyclic prefix, transmit over the channel, at the receiver, remove the cyclic prefix, parallelize it, FFT, then employ a detection, a coherent detection essentially to remove the effect of the channel, all right, and then you serialize it and multiplex it back again to the application. So that is the OFDM schematic. It's very simple in the sense it's a very low computational complexity as we have already seen, because it employs simple IFFT, FFT operations which can be implemented for a large number of subcarriers, that is n equals 1024, 2048 also. And that is the reason why we said, remember earlier we said that these number of subcarriers have to be a power of 2, and now you can clearly see the reason. That is because we are employing an IFFT and FFT, and these algorithms, we have fast algorithms for FFT in case essentially the number of points in the FFT is a multiple of 2. Hence typically the number of subcarriers one employs are 256, 512, 1024, 2048 depending on the scenario. So what we are saying is, while employing this OFDM system, we have successfully converted this, and of course intelligently employing the cyclic prefix, which is not to be forgotten, we have converted this wideband channel, which is a frequency selective intersymbol interference limited channel, into something that is looks like a flat fading channel across these n subcarriers. All right, so that is the biggest advantage of OFDM. Let me come back to talk a little bit more about the cyclic prefix. Let me talk a little bit more about the cyclic prefix. Now remember, in the cyclic prefix what we are doing is we have a sequence of OFDM. These are the OFDM samples. We have a sequence of OFDM samples. What we are doing is we are taking some of these samples and prefixing that. That is, we have xn minus 1, xn minus 2. Now remember, the first thing I want to point out was how many such symbols, cyclic prefix do we need? We at least need number of symbols equal to roughly of the order of the delay spread. Remember, we need at least L minus 1 symbols to avoid symbol interference from the previous OFDM symbol. So the minimum number of such samples, minimum length of cyclic prefix, so the minimum length of cyclic prefix required is L. In fact, you can see that this is related to the order of the delay spread, or in fact to be precise it is L minus 1. This is the delay spread. In fact, the delay spread is L. This is related to the delay spread of this channel. In fact, cyclic prefix should be greater than, ideally it should be greater than the delay spread of the channel. I want to emphasize this. This is key. Remember, we said in a wireless communication system the channel has a delay spread, that is, energy is not arriving at a single point of time, but it is arriving in a delay. That is what gives rise to this intersymbol interference and this FIR filter of channel taps of delay spread L, because signal energy is arriving across the spread. Alright. So, what we are saying is this cyclic prefix that is added here, this is the cyclic prefix, this length has to be greater than the length of this cyclic prefix has to be greater than the delay spread. In fact, the larger it is, the better it is. Alright, or I will simply write it as greater than or equal to L. Alright, and this is to avoid OFDM symbol interference. This addition of cyclic prefix is, as we said, to avoid inter OFDM symbol interference. So, this is to avoid inter OFDM symbol interference. Okay. However, there is a catch here. Remember, because of addition of cyclic prefix, we are transmitting these symbols xn minus 1, xn minus 2, so on twice. That is, we are transmitting them once as the OFDM samples, once we are transmitting them as the cyclic prefix. So, what we are doing is we are simply taking these symbols and repeating them. Now, although x0, x1, xn minus 1 are information symbols, simply repeating them will not convey any additional information. So, the idea that I want to bring about here, simply repeating information symbols, repeating symbols does not, that is the keyword, does not constitute information. Alright. What is information? Information is new symbols that the receiver have not seen before, which encodes information. If I am simply repeating the same symbols, there is no information. In fact, there is loss of spectral efficiency, there is a loss of bandwidth, because you are transmitting the same symbols. Hence, what we are saying is the addition of cyclic prefix results in a loss of spectral efficiency, loss of efficiency, or loss of effective throughput in the systems. Hence, the catch is, the effect of addition of long cyclic prefix is loss in throughput of the system, loss in hence that is the catch. Essentially, that is the catch. What is the catch? The catch is essentially we would like to have a longer cyclic prefix, much greater than the delay spread of the channel, so that you can protect against intersymbol interference. However, the moment you start using longer and longer cyclic prefix, what you will have is cyclic prefix becomes dominant, and then you will start losing in terms of effective throughput of the system. So, there is a trade-off in terms of cyclic prefix versus the throughput of the system. One has to manage the length of the cyclic prefix such that the throughput does not get affected significantly. In fact, the loss in efficiency is nothing but cyclic prefix by the total symbol length. Which is equal to, we know that the cyclic prefix length is nothing but L minus 1 The total OFDM symbol length is OFDM samples plus cyclic prefix, which is n plus L minus 1. Now we can see we have one additional parameter in this, which is n, and we see as the number of subcarriers n increases. So this is the loss in spectral efficiency because of addition of cyclic prefix, and we can see as n tends to infinity, L by n plus L minus 1 tends to essentially tends to 0. So we can see limit n tends to infinity, L minus 1 divided by n plus L minus 1 tends to 0, implies the loss in spectral efficiency approaches hence what this says is one has to employ progressively more and more subcarriers. So the larger the number of subcarriers, the better it is, so that the cyclic prefix doesn't result in loss of throughput. So larger number of subcarriers, so hence larger number of subcarriers, hence larger number of subcarriers implies lower loss on susceptible system throughput, lower loss of hence the larger number of subcarriers implies essentially a lower loss of system throughput. Hence what we are essentially saying is, now as n increases, remember the OFDM symbol time is n over b, that progressively increases. As n increases, OFDM symbol time n over b, which is the large OFDM symbol time, that increases. As n increases, the OFDM symbol time n over b progressively increases. Hence what we essentially have is, let us say we have an OFDM symbol and this is the OFDM symbol time, and this is the delay spread, which essentially affects the as affected by the intersymbol interference. This is the intersymbol interference affected part. This is essentially what is the n over b parts. Now what we have is, as n over b increases, this part progressively becomes much larger, and we need a delay spread, cyclic prefix length equal to delay spread. Hence what we have is the fraction that is affected by intersymbol interference. So this is larger as n increases, the OFDM symbol becomes larger, hence a smaller fraction is affected by intersymbol interference. Hence as n increases, progressively smaller fraction is affected by ISI. So what is happening is, as n is increasing, a smaller and smaller fraction is getting affected by ISI as the symbol spread is increasing. Hence one can also think of this as n by b. Increasing n by b compensates for the ISI arising out of the delay spread. Hence we can also think of the increasing n results in increasing OFDM symbol time which compensates for the ISI. So, ISI becomes a progressively smaller fraction which comprises for the ISI arising out of the delay spread. However, what is the trade-off in increasing n? Remember, you have to wait till all the OFDM symbol is received to decode all the subcarriers, which means as you increase n, the decoding delay is increasing. Hence, as n increases, the decoding delay of the system increases. As n increases, the decoding delay of the system increases. Hence, the trade-off to increasing n is trade-off. Hence, there is a trade-off versus increasing n versus decoding delay. Hence, for n versus the delay, and more specifically versus the decoding delay, or essentially the data delay. Hence, that is the trade-off. If you increase the number of subcarriers to a very large number, you will have progressively more and more delay in decoding all these OFDM symbols, which might not be suitable in some applications. Let's say you have an audio or video application which requires fast data to be decoded. For instance, if you are watching a movie, you have to have streaming video, you have to have a frame that is decoded every so and so time. You cannot have a large time interval or a large delay for decoding these symbols. Since that is, the decoding delay is also a very important parameter in systems, especially 4G wireless systems. All right. Also, let's look at one intuitive understanding of this. Let's look at an intuitive framework. Let's look at an intuitive framework. So, this is an intuitive framework to essentially understand the cyclic prefix or CP. We are saying that the number of symbols in the cyclic prefix, or NCP, so the number of symbols in the cyclic prefix NCP has to be such that the number of symbols into symbol time has to be greater than or equal to the delay spread. Remember, that is what we are saying, the length of the cyclic prefix or the duration of the cyclic prefix should be greater than the delay spread. Cyclic prefix has n symbols, each is of duration Ts, which is the symbol time, that is 1 over b, that is the sample duration. So, NCP into sample duration should be greater than the delay spread, which means NCP should be greater than or equal to Td over Ts. Now, remember, we already said the symbol time is nothing but 1 over b. So, 1 over Ts equals b, and we said Td, the delay spread, is nothing but 1 over twice the coherence bandwidth. So, this is equal to 1 over 2 Bc. Hence, what we are saying is NCP greater than or equal to b by 2 Bc. So, what we are saying, the first thing we are saying is intuitively NCP should be greater than half b by Bc. Let's this is number of symbols. This is the number of symbols in the cyclic prefix. This is the bandwidth of the system. And this is the coherence bandwidth of, and this is the coherence bandwidth of the system. So, we are saying To avoid intersymbol interference, number of cyclic prefix has to be greater than, number of symbols in cyclic prefix has to be greater than half B over BC. Now also we said for spectral efficiency n is much greater than this cyclic prefix, the number of cyclic. So for efficiency on the other hand, we require n much greater than NCP, which is greater than or equal to half B over BC. Hence what I am going to say is, since n is much greater than NCP, which itself is greater than half B over BC, hence I will roughly say n has to be much greater than B over BC, where n is the number of subcarriers, this is the number of subcarriers, this is the bandwidth of the system, this is the coherence. This is the coherence bandwidth of the channel. N is much greater than or equal to B over BC, and now I have something very interesting. So I look at n much greater than B over BC, I rearrange these terms, which means now taking BC to the left, I can write this as BC is much greater than P over n, and this is a very interesting result. This is the coherence bandwidth, it's much greater than B over n. And what is this B over n? Remember, B over n is nothing but the subcarrier bandwidth. So in this, these two terms as follows, this is the coherence bandwidth, this is nothing but the bandwidth of each subcarrier, this is nothing but the bandwidth of each hence what this means is, as I increase n much larger than the delay spread in terms of number of symbols, the subcarrier bandwidth is less than the coherence bandwidth. So what this means is, subcarrier bandwidth is less than the subcarrier bandwidth is less than the coherence bandwidth, which essentially implies that each subcarrier experiences flat fading. Remember, that is our main aim. We said we want to arrive at a scenario such that the subcarrier bandwidth is much less than the coherence bandwidth. Now this shows a limit on the number of subcarriers, such subcarriers. It says that the number of subcarriers, such subcarriers has to be chosen such that it is greater than the cyclic prefix, all right, which in essence is related to the bandwidth and the coherence bandwidth of the system. So this implies each subcarrier experiences frequency flat. So by increasing n as described above, what is essentially happening is each subcarrier experiences frequency selective fading. Hence, an appropriately designed OFDM system converts a frequency selective fading channel into a set of parallel flat fading channels across the subcarriers. Let me just note down this final point. Thus, an appropriately designed OFDM system converts a frequency selective fading channel with ISI converts a frequency selective fading channel into a set of parallel flat fading narrow band channels. Converts a frequency selective fading channel into a set of parallel narrow band flat fading. Alright, so the appropriately designed OFDM system converts a frequency selective fading channel into a set of parallel narrow band flat fading channels across the subcarriers. In fact, let me add here across the subcarriers. All right, so that is essentially a technical perspective on OFDM. Let me now just go on to a simple example to illustrate this point better. So let me go on to an example of an OFDM system. So let's go on to an OFDM example. So let's consider a 4G wireless system. In fact, what I'm going to consider is I'm going to consider an example from WiMAX. So let us consider an example of a 4G wireless system. In fact, I am going to consider WiMAX. As we already said, WiMAX is a 4G wireless standard. WiMAX stands for Worldwide Interoperability for Microwave Access. This stands for, in fact, I have this stands for Worldwide Interoperability for microwave access. And I want to consider WiMAX or this WiMAX based on, and WiMAX is in fact, as we already mentioned, and you have to and it goes without saying, 4G systems are based on OFDM system. WiMAX is based on OFDM. That has to be clear. So far we have mentioned several points in the course that all 4G cellular standards are based on OFDM. WiMAX is in fact based on orthogonal frequency multiplexing. In fact, WiMAX has several profiles. So WiMAX has several profiles which are essentially usage set of parameters for usage. So WiMAX has several profiles. So one of that profile is known as a fixed WiMAX profile, which is essentially used for fixed wireless access. So we are considering the fixed profile of WiMAX. So let us consider the fixed profile of WiMAX, which is essentially used for fixed wireless access, where wireless devices are fixed. These are not mobile. All right, and this profile of WiMAX has n equals 256. This profile of WiMAX has n equals 256 subcarriers. It is a 4G standard, and the subcarrier bandwidth equals 15.625 kilohertz. So the bandwidth of each subcarrier is 15.625 kilohertz. All right, which essentially implies B by N. Remember, B by N, subcarrier bandwidth is nothing but B by N. B by N equals 15.625 kilohertz. All right, so we are considering the example of a fixed profile of WiMAX, which is a 4G wireless standard. that has one profile is the fixed profile, which has n equals 256 subcarriers, and the subcarrier bandwidth is B by n is 15.625 kilohertz. So at this point I will stop this lecture because of shortage of time, and we will again continue starting from this point in the next lecture. Thank you very much for your attention.